Hey space fans! Starship Flight 12 is still floating. The Chinese are about to send hopping robots to the moon. And we talked to Dr. David Kring of the University Space Research Association about how, where, and why the Artemis program will be doing science on the moon. Stick around.
Podcasts you love.
From people you trust.
This is Twit.
This is This Week in Space, episode number 224, recorded on August 21st, 2026, The Science of Artemis. Hello, everyone, and welcome to yet another episode of This Week in Space, The Science of Artemis edition. I'm Rod Pyle, editor-in-chief of Ad Astra Magazine, and I'm here with guest co-host, Dr. Rick Chang'e, who's the founder and CEO of Expanding Frontiers, vice president of technology and entrepreneurship of the National Space Society, and also on their board of directors. So he's important to me because he's one of the people that waves his hands over my paycheck. Hi, Rick.
Hey, Rod. Great to be here.
How are you?
Oh, not too bad.
I just gave you an organizational promotion there. Today we're going to be speaking with Dr. David Kring from the University's Space Research Association about the science of the Artemis program, what we're looking to discover, how we'll do it, where we'll do it, and a lot more. So I think you're really going to enjoy this one. But first, before you start enjoying yourselves, let me put a crusher on your spirits by telling you a new space joke from listener Steve Werzer. Last week, an alien spaceship crashed in Las Vegas. When the police arrived, they found Elvis unconscious at the crash site. They rushed him to the hospital, and when he woke up, the doctor asked, "How are you feeling?" And what do you think Elvis said, Rick?
I don't know.
He said, "I'm all shook up."
Oh boy.
Okay, thanks for the kind rim shot. I didn't deserve that. Now,
I think the jokes are getting better, Rod.
Or do you now? I've heard that some people want to shake us at Adams when it's joke time in this show, but you can help, please, by sending us. And actually, Steve, I appreciate that. That was a pretty good one. But you can send us your best, worst, or most different space joke at twist@twit.tv, and we'll tell it on the air, and we'll blame it on you if it goes over like some do. All right, but for now, let's do an abbreviated headline news.
Headline news.
Headline news.
Oh, there you go. Thanks for that, John. So, gosh, Rick, Starship test number 12 and the Starship itself, which touched down the Indian Ocean but did not explode, shockingly, has been at sea for a long time. I think it's been at sea longer than some freight journeys take. And shockingly, they've actually been able to keep it in one piece while they slowly towed it back. And I gather it's now sitting just offshore at Christmas Island near Australia, is it? Or New Zealand? Australia. So I guess it's kind of important that we got to look at that at the very least so they can see what happened with the heat shield, right?
I think that's one of the key issues. I just think of it, the amazing engineering feat that went behind that it's still, keeping water out. It's never easy, especially saltwater and saltwater conditions. So kudos to the engineering team there for what they did.
Yeah, and structurally, obviously anybody who knows anything about engineering knows this, but you have to construct these things very lightly. It's always shocking when I see a genuine spacecraft and get in there and start knocking my knuckles on things. They're lightly constructed because they're rockets and they have to fly and they're supposed to carry a ton of fuel. So it's a bit surprising when you actually start, you go to something like the Apollo lunar module and put your finger, which I've done once, I wasn't supposed to, on the main pressure hull and go badoink like that because, a lot of parts of it are pretty thin. And Starship is a big, thin stainless steel structure. So kudos to SpaceX engineering for keeping that thing in one piece. And fingers crossed their next test flight. All right. And coming up, we have the launch of China's next great robotic mission to the moon, Chang'e 7. Which in this case has a lander, a rover, and a hopper. And where are they going?
So I'm very excited about this mission. I think China is once again going to show its prowess in lunar exploration and just how far that they're able to succeed. And they're going to go into a permanently shadowed terrain. First time, at least in my memory and background, first time that humanity will have ever done anything like this. So it's going to be pretty exciting to see what they find.
Yeah, it is. And each of these missions gets more and more ambitious. And, there was a lot learned by the Soviet Union and the U.S. back in the 60s and 70s. I always rant about this, that you can borrow the technological know-how from. But the Chinese have taken that, as they often do with technology, and really honed it to a sharp edge, and are doing amazing things, new things with each mission, not the least of which was being the first to land something on the far side of the moon and put up the 2 Magpie communication satellites so they could actually talk to it, because otherwise you can't do that. So this will be impressive. And also, nobody's done a hopper before. It was discussed. It was planned, but never happened. I don't know how much fuel it carries and how long it could do what it does. But in the lower gravitational field of the moon, that's going to be a very cool thing. All right. And lastly, we have the whopping big National Space Transportation Policy that came out earlier in the week, I guess.
I think it was yesterday.
Well, was it yesterday?
Yeah.
Tell us
August
what it
20th.
said that caught your eye.
So the administration wants U.S. infrastructure to support more than 1,000 launches and re-entries per year by 2030. That is an exciting number.
It sounds kind of like an arbitrary number in some ways.
Well, it is 1,000. It's not like 936.2 or something like that, but it's definitely a nice round number. It's hefty, but if we are, if they're going to take commercial space seriously, if we're going to take, humanity and the United States developing a space presence, we have to move into this phase where we are doing hundreds of launches on a monthly basis. So. I guess we can all say, it's like, well, is this real? Is it not real? But at least there's a goal in place, and at least it's being discussed at the highest level. So that's what that's what I see as being exciting, that this is actually being discussed seriously, and setting, drawing the line and setting the goal. So.
Now, I often get a bit of a slap down if I say anything political on this show, so I try not to, but what puzzles me is these kind of directives coming from in an era, let's just say, where NASA was basically shoved in a box, shaken up, and then half of it poured out and left to rot in the sun. And the 70% or so of the agency that's still in place and effective, that's a very gross guess, is now charged with this new thing. I mean, I'm all for it, but if you're going to do that, it's probably not the best thing to jettison 20-30% of your top people and your most senior minds. You can argue that, there were some people that probably need to be cycled out. You see that in any endeavor, whether it's private industry or government, and that, you want to bring in young blood, but that wasn't the directive here. It was just cut, trim, doge. And a lot of people weren't replaced until recently, and we're still seeing the beginnings of this, when Jared Isaacman said, okay, we're going to stop working with so many contractors and bring more people back in on staff, which is fine, but it kind of puts them back where they were in a slightly different way, if that makes sense. Do you have any thoughts on this?
Well, it's interesting that this is a U.S. national space transportation policy. So I think what you're pointing at is they're not going to necessarily lean on NASA to do this, and what they're hoping is that the commercial entities are the ones that take this up, and we do need we know we need dissimilar redundancy in our launch systems, so we have to promote it somehow. And until we get to commercially sustainable business plans for space development, the government is going to be funding this somehow, one way or another. And I kind of see this as a move in that direction. It's like, all right, let's at least say that this has to be, we need to have the infrastructure to support this, and that's just coming from, from the administration, or at least from that level.
Yeah.
How exactly it gets implemented, that's going to be the interesting question. And does this mean this is going to promote other launch systems and other launch companies coming into this space? No pun intended. I hope that it actually does. And in some sense, like what you said, a lot of very good minds were let go from government service. Because of this, a lot of them might actually find homes in some of these commercial entities. So overall, I definitely think it's a positive thing for space development.
That last point of yours kind of strikes home for me. I was talking to some senior people at JPL recently, and and they were not trash talking private industry at all. In fact, they're all in favor of it, and NASA's been kind of pivoting this direction since about 2010, where they want to use more and more private vendors. What we have suffered from a bit, though, intuitive machines, was a little bit of what I and other people would call hubris on the private side when designing, say, something that's as thought to be as simple as a new lunar lander. We have a lot of engineering knowledge starting from the 1960s, when the Surveyor spacecraft with nice wide footpad stance at a low center of gravity landed on the moon and stayed upright. And then we had a series of missions that landed on the moon, didn't stay upright. And there seems to be a failure of learning there. And a number of the NASA people I've talked to are on advisory boards, for instance, with some of these organizations, and have said, you might want to look into this and look into that. And in some cases, those suggestions were warmly embraced. And in other cases, my sense indirectly is that they got kind of yeah, that's nice. Don't worry your pretty head. We're young engineers and we like to move fast and break things. The problem with breaking things in space is it's really expensive. It's not Facebook, where you have a software error that you can then round off a couple minutes later. It's obviously all the way out to the moon, lunar orbit, or on the surface, or near Mars or something. And when things fail out there, it costs a lot. So I guess what I'm whining about here is I would just like to see a little more embrace of the hard-won knowledge of the first space age. When we learned how to do this stuff, it was expensive as hell. But there's a lot of knowledge there that can be scooped up, and you don't always have to do it in a new, bright, shiny way. All right.
Well, humans are always going to fall into the trap of hubris. That's just what's going to happen. But hopefully, and like you said, it's not Facebook where you can just throw something together, see if it works, and fail fast. But I do think we have to get ourselves, if space will really take off when we are at that point where we can iterate very fast and we can try different things out, and the cost isn't there that much. Hopefully, in the next decade or two, we'll be at that point, and then things will really take off. But I think that is an important point of us moving forward in this thing, is that we do have to learn how to fail fast and fail often. And some might claim that the current success stories we're seeing live that mantra.
Where might you have encountered hubris in your recent career, Rick? No, I don't want you to answer that. I was just kidding. That's a rhetorical question. All right, we will be back in just a few minutes with Dr. David Kring, so stay with us. And we are back with Dr. David Kring, who is the principal scientist for lunar programs at the University Space Research Association and director of the NASA Space Imagery Center at the Department of Planetary Sciences, Lunar and Planetary Laboratory, University of Arizona. Is that second credit past tense or present tense?
That's past tense, so you want to scrap that.
Okay.
Yeah,
Did I miss anything, though?
So the USRA title is good. You could add that I was recently a fellow at the Harvard Radcliffe Institute in Cambridge, Massachusetts.
Well, it doesn't sound to me like you need any more credits, but clearly you have them. And as I was scrolling down the page of your achievements, I thought, I need to pick one or two of these instead of the 10 or 20 that are listed here. But thank you for joining us today. We do appreciate it. We're here to talk primarily about the science of the Artemis lunar landing program, what we want to do, what we want to learn, and how we're going to do it. So I guess I'll start with the fact that the USRA has conducted lots and lots of research on this topic and generated a number of important papers. So maybe we could start with where we go. What characterizes in your mind a good candidate for a lunar landing site besides safety and geological interest?
When you select the final landing site, of course, you have to take into account not only the scientific objectives, but what the hardware can accommodate and where that hardware and crew capabilities are in the development of a new era of lunar surface exploration. There's two, from a scientific point of view, there's two ways to look at this. One, during the Constellation program, which preceded Artemis, NASA went to the National Academy of Sciences and asked what are the nation's science priorities, and they produced a wonderful document. It's published in 2007 called roughly the scientific objectives for a new era of exploration on the lunar surface. And we actually spent 6 years evaluating that document and where on the lunar surface that you could accomplish that science. And we did something completely unique. We did it objectively. That is, there were 8 goals and about 35 investigations in that report. And we took each one of those investigations and we said, where on the lunar surface can you address this investigation? And there's, dozens, if not hundreds of sites for each one of those investigations. And at the end of that 6 years, we then stacked those maps and we asked ourselves, where could you accomplish the most science and the most high priority science? And the answer was the Schrödinger impact basin on the lunar far side. And so from a purely academy level science perspective, the Schrödinger impact basin is where we should be going. Now, that's not where we're going. The Artemis program was languishing in schedule. And so the vice president of the nation says, well, I'm going to help you out. You're going to land at the lunar South Pole. And so the Artemis exploration zone, at least the initial Artemis exploration zone, is within 6 degrees of the South Pole. And knowing that, we've now conducted, again, 6, 7, maybe even 8 years now of studies of that region and published, as you noted, about 24 peer-reviewed studies of potential landing sites in that area. The science is going to be different. That's all there is to it. And we can talk more about those science objectives if you would like.
So I'm curious. Of course, there's always the scientific value and how we're using resources to get the most science, and that's was one particular approach that you were just mentioning there. But then, of course, you mentioned another one, which was NASA said this is where we're going, which I think is an interesting piece there. I'm curious, what do you think is driving that? Is it resources, commercial, water?
Yeah, well, actually, it was the vice president, not NASA, that said where we're going, and NASA said. Oh, yeah. And so we're going to the lunar South Pole, polar region, at least as it's configured today. As we speak, there are discussions of maybe landing elsewhere for the first or second mission. But at the moment, we are targeting the lunar South Polar region, and that was driven in part by resources. And there's 2 different types of resources that NASA has now highlighted. One of those is solar power. In the South Polar region, actually, let me take a step back. During Apollo, we were landing in the equatorial region on the near side. And in that portion of the moon, the sun is rotating overhead every 28 days. And so you have 14 days of daylight and then 14 days of darkness. And that 14 days of darkness is a challenge to survive. And so the polar region is attracted in that the sun is orbiting the polar region just a few degrees off the horizon. It doesn't set unless it passes behind a peak. And so there are locations in the South Polar region where sunlight is always present for 86% of the time. And the duration when you do not have access to solar power are quite short. And that's attractive to mission architects. The other resource I want to. The solar resource is a known. It's there. How we harvest it, how we distribute it are issues I think that are still being worked out. But there's another resource that is a potential resource, and it's going to take some exploration to verify its presence and whether it is actually recoverable, and that is volatiles. So there have been models since the 1960s that in the polar regions, there are permanently shadowed areas where the temperatures are quite cold, and volatiles like water ice and carbon dioxide ice, dry ice as you know it, and other gases might be trapped. And if that's the case, that would be very useful. So, for example, the water, if water could be recovered, that would obviously be useful as a crew consumable. Water is a very useful shield against space ionizing radiation. And third, you can break up the water and form rocket propellant, which can move you about the lunar surface or take you off the moon to deeper solar system destinations. So those resources, or potential resources in the case of volatiles, I think are what's driving a lot of attention in the South Polar region.
We're going to go to a break in a couple minutes, but just a short one. What's very attractive about the Schrödinger impact basin?
Schrödinger impact basin, it's a marvel. Well, first of all, in that original NRC 2007 report, the first and second highest priorities for lunar science was to test the idea that the moon and the Earth and the entire inner solar system had been severely bombarded by asteroids and comets early in solar system history. And so to test that, you actually need to go to some basins and determine their radiometric ages. And the Schrödinger impact basin is the second to the last basin formed, and so it has not been overprinted by impact events that occurred later. That is the things that has vexed us with the Apollo samples. They're messed up. And in addition to Schrödinger being the second youngest, it actually is within the largest impact basin on the moon, the oldest impact basin on the moon, which is the South Pole Aitken Basin. And so we're hoping in one location to get the ages of both. And then later, the volcanism spewed lavas and pyroclastic material out on the surface. Our calculations indicate that that is the largest indigenous source of volatiles in the South Polar region. So if we do find them in the South Polar region, many of those volatiles, in fact, may have come from Schrödinger. And basically, most of the objectives in that NRC 2007 report can be addressed. They may not always be resolved, but you can address a majority of those NRC 2007 objectives within the Schrödinger impact basin.
All right, we're going to go explore our way into a break, so we'll be right back. Go nowhere.
So, David, first off, I didn't get a chance to say before I started asking questions, just how excited I am that you are here to join us. And I definitely enjoyed learning more and more about what you've been doing in your career. It's been very exceptional, to say the least. And I really thank Rod for giving me the opportunity to be able to talk to you about these, everything that's going on the lunar surface and so forth. Something that you may be aware of course, is the United Nations Office of Outer Space Affairs and the Committee on the Peaceful Uses of Outer Space. And in that is this committee of ATLAC, which is the Action Team for Lunar Activities Consultation. So we know that lunar surface exploration is heating up, if you will. And there is a very interesting conversation at those levels, which has to do with protecting science on the lunar surface. And I'm curious to see what your thoughts are about, do we need to have protected zones on the lunar surface to protect science? Or is it not necessary? Is there another way of doing that, or anything? I'm just curious about what your thoughts might be there.
That's a tangled area. It's a little bit outside of my expertise. At the end of the day, I think the answers to those questions will depend on how many missions to the lunar surface there are, and we can talk about that on an annual basis or decadal basis, because each one of those landers is disturbing the lunar regolith. And not only is it disturbing it in the local area of the landing, that material gets plumed and can be distributed globally. Okay, and so that can have a consequence on areas far, far, far from the impact, the landing site. And that is particularly true for the largest landers. So we did do a calculation, and I have to acknowledge that this is a preliminary calculations because we don't yet know the final specifications of the SpaceX human landing system, but that appears to have a dramatic pluming effect and will definitely distribute material globally. So we can refine those calculations once we better understand what that lander's final configurations will be. But that preliminary calculation illustrated immediately that this has a potential consequence for landing sites far, far from your base of operations. And then there has been, in the meetings that I have attended, discussion of recovering a lot of these components, such as, volatiles of various types. And then the question is, how do you recover those volatiles? And if you are doing basically the equivalent of shaft mining, the consequences will be rather limited. If, on the other hand, you are having to strip mine multiple hundreds of kilometers of the lunar surface, that's a completely different ballgame. And we don't know between those extremes where reality will land. So I'm glad that the conversations are going on, and because that means people are mindful of the potential problems, and they will monitor those activities and see where they do in fact land and what the potential consequences are. Yeah, I don't know that we have the capability to make rules or regulations without better understanding the scope of the activity.
No, fair enough. And no, I agree that it's exciting to be living in a time where people, delegates, state actors are at the point where they feel it is necessary to have these conversations. But I guess going back to something that I'd love to hear your opinion on related to the science, and I'm sure being an astrophysicist myself, there's always kind of the holy grail. Be like, this is the thing that I would love that we could see or discover that could really change like everything. Do you have something like that? But like here, like this will change lunar science, or
no. I mean, this we have explored a very tiny portion of the lunar surface. And so basically the Artemis exploration zone, or any place on the far side, with the exception of the small region that China recently explored, is unknown. And so anything we do is by definition going to be exploration and in a land of discovery. And I don't know that you can predict what those discoveries will be. What I can say is that Apollo demonstrated that the key to transformational science is the collection of samples by well-trained astronauts and the return of those samples to Earth. Because it's only in our terrestrial laboratories where we tease them apart. And so just think about the big ideas that you hear about on the Discovery Channel, the Learning Channel. It's the giant impact hypothesis for the Earth-Moon origin. It's the lunar magma ocean hypothesis. That is the idea that the moon was once surrounded by an ocean of magma. It's the lunar cataclysm or inner solar system cataclysm hypothesis. And that one's huge. I mean, not only has that one taught us that all of the inner solar system was being blasted, including Mars, but that may have been prompted by the accretion and orbital evolution of the outer solar system planets. And so the record of those events, the record of those processes are best preserved on the moon. And so it's an extraordinary place. And so I think that one of the key things that we have to remember is that samples have to be a high priority. And right now, sample return is not a high priority. And that, in my mind, threatens the capability of outstanding Artemis science.
That's very interesting. Why don't we quickly bombard our way into a break, and we'll be right back. Stand by. So, David, we're talking about the south polar region of the moon, which has some unique challenges. You've got eternal sunlight in some areas and eternal shadow in some other areas, and brief periods of transition in some other areas. But it's really very different in those ways, survivability in particular, but also visual acuity and so forth in the Apollo landing sites. But in your mind, having studied this extensively, what are some of the unique challenges of pursuing the kind of science you want to do in a polar region versus what we did with Apollo? And how will that be different from what we did during the Apollo program?
Well, one of the first things I try to explain to the engineers at the Johnson Space Center and those in the astronaut office is that the topography in the lunar South Polar region is huge. I mean, it is almost mind-boggling. So the South Pole is sitting on the rim of a crater called Shackleton. That crater is 3.5 times deeper than the Grand Canyon. Not too far away is a mountain summit called Malapert, and that towers higher than Mount Everest. Okay, and so within very, very short distances, you have just an amazing amount of topography that I explained to people in public lectures. If it occurred on the Earth, it would be a national park. It's going to be incredible. So topography is going to be a challenge. Climbing hills, it's going to be a problem. I'm not too worried about the light or the shadows. I think the topography is the bigger issue from an operational point of view. Now, from a scientific point of view, that South Polar region is far more ancient than the Apollo sites. That's exciting. We'll probably collect samples of rock from an earlier phase of lunar evolution than we saw in the Apollo sites. But it also means, and we learned this from Apollo 16, that repeated impact cratering, which is what you have in those ancient terrains, really makes it difficult to tease apart the geologic stories. And that's one of the attractiveness of Schrödinger. It's late, it's simple, we'll get the answer, it'll be clear. There's going to be a lot of debate, and I suspect some heated debate amongst scientists analyzing Artemis samples from the South Polar region because of the complexity that those impact cratering processes produced in that region.
Well, you mentioned Apollo 16. I wanted to mention that is the mission during which we had the most elevation change in those explorations. The longest EVA on Apollo was about 8 hours. But the highest they ever got, or the most elevation change they ever had, was 500 feet, which is a far cry from the kind of dynamics you're talking about doing double and triple the Grand Canyon. So this is going to be quite different in scale than what we did with Apollo, isn't it?
Yeah, well, yeah. So they're obviously, the astronauts are not going to be able to walk into those depths or to those summit horizons. So they'll be limited in their excursions. And, the walking EVA limit is currently 2 kilometers. At the moment, Artemis does not have the communication capability to allow them to go 2 kilometers. Now, once we get mobility assets on the lunar surface, the distances that crew can go might be 10 or 20 kilometers from a landing site. The objective is, as mission cadence increases, is to land those mobility assets, let the astronauts use them in that area, bring the crew home, and then teleoperate those assets to another location. And those mobility assets will do the climbing. And then the astronaut, once they're in their new location, the astronauts can land at that alternative landing site. And in fact, we were asked by NASA to do a very lengthy traverse study across the South Polar region into the center of the South Pole Lake and Basin on the lunar far side with that type of architecture in mind. And we did find a route where 2 crew rovers could traverse that entire distance, and then the crew could meet those rovers in 5 different locations and conduct independent short-term missions at those locations.
That's interesting. Rick?
Well, I'm curious, how much of the Artemis planning, these traverses and so forth, do you think should be done in advance, and how much should be left to, the actual astronauts on the ground and, using their own judgments when they're there?
Oh, the basics of the traverses initially will be laid out, I believe, by the geologic team working with the crew. But the astronauts will, at the scale of features visible to them and only them, will then be making independent decisions. And that's why they have to be well trained. I mean, it's absolutely essential that we utilize all available data in initial traverse planning, that the geology team supporting the astronauts themselves have well-documented experience, and then third, that the astronauts themselves are well-trained for the type of missions that they're going to be conducting.
So you've done a lot of work on craters, everything from Chicxulub, which is the big dinosaur killer down in Latin America, which is about 120 miles across, which is large, down to Meteor Crater in Arizona, where you've done some significant work. And my understanding is that, one of your conclusions was that the Arizona Meteor Crater, or Barringer Crater as it's sometimes called, is a good analog for studying how to do this kind of work and these kind of traverses. Have you done that work there?
Yeah, no, absolutely. It was, not surprisingly, it was used by Gene Shoemaker during Apollo to train the astronauts. It's a crater, by the way, for those who know Apollo. It's very similar in size to North Ray Crater at the Apollo 16 landing site, about a little over 1 kilometer in scale. And I've trained most of the flight active astronauts when they were candidates at Meteor Crater. And yes, it's wonderfully preserved. Anybody who wants to get some sense of what it's like on the lunar surface should visit Meteor Crater. One of the things I point out to the astronauts is that topography is king. So if you go in and out of that crater, you better understand what you are asking crew to do if they were to go in and out of a crater of that size. If you listen to the voices of the Apollo 16 crew, they had no interest in going into North Ray Crater. In fact, they were a bit, they didn't even like getting close to the rim. But the other thing that I point out when we're on the rim of Meteor Crater is, going back to the Apollo 16 landing site, is that in the immediate vicinity at North Ray Crater were 2 other craters exactly the same size. We have this false sense of crater density on the lunar surface, on the Earth's surface, because they are so easily eroded and buried and otherwise destroyed, whereas they've been accumulating for over 4 billion years on the lunar surface. And so astronauts, as I explained to them, they will not be able to take a single step on the lunar surface without stepping into or onto an impact crater. It's just impossible. And so any operations on the lunar surface have to understand the fundamental processes of impact cratering and what it does to that surface.
Well, that sounds like a bit of a challenge. And I do remember, because I'm old, listening to the EVAs for both Apollo 15 and Apollo 16. And what I remember about Apollo 15 was Dave Scott kind of encouraging everybody, hey, we really ought to drive a little further down into this into this ravine, and Mission Control saying, we might want to think about that a little bit. And at one point, the rover started to tip, and I think it was Irwin had to put his foot on it to hold it in place. These are my recollections anyway. But it was a pretty exciting time. But again, in terms of the magnitude of what you're talking about here, not quite as ambitious. Let's run to a break, and we'll be right back. So stay with us.
Okay. Well, so when we hear about craters and impacts and so forth, we know that in one way or another this affects life, or at least it had affect life on Earth. And I'm curious about whether the moon can tell us, and the impacts on the lunar surface can tell us anything about how how such impacts helped life begin on the Earth's surface.
Yeah, early in my career, our team found the Chicxulub impact crater, which is key to the impact mass extinction hypothesis. And what I realized as I was studying those Chicxulub rocks is that the impact also generated this vast subsurface hydrothermal system beneath the floor of the crater. And it occurred to me during the early solar system history, when the Earth was being just bombarded by asteroids and comets, that those impact events were sometimes completely vaporize the seas, or simultaneously producing these vast subsurface hydrothermal systems beneath the surface. And those are perfect crucibles for prebiotic chemistry and the early evolution of life. So that's the impact origin of life hypothesis. Now, we've been testing the heck out of that. In fact, just this morning I was adding up how many papers. We have 35 papers have tested that hypothesis, and we've shown that microbial ecosystems can exist within and below the floor of the Chicxulub impact crater. But to then take that model back in time, you want to better understand the cadence of impact cratering. You want to understand the magnitude of those impact events. And ideally, you'd like to understand the composition of the impactors producing the craters. So at the moment, what we have gleaned from our studies of the lunar surface is that at that time, 85% of the impactors were asteroids, and about 15% were comets, which is basically the same values that we have today. We've also, by looking for fragments of these impactors in the lunar soils from the Apollo sites, they seem to be concentrated carbonaceous chondritic type of meteoritic materials, which are the ones that carry the sugars and the amino acids and so on and so forth that you oftentimes hear about in the news. Now, we've only collected those types of samples from a few areas on the near side of the lunar surface, so we would certainly like to look for those types of materials elsewhere, such as the South Polar region of the moon. The other thing is a tease. During that period of bombardment, things were hitting the Earth at the same time they were hitting the moon, and some of that material was getting jettisoned from the Earth and hitting the moon. And so the oldest fragments, the oldest surviving fragments of the Earth may be on the moon. And in fact, in 2015, we actually published a paper. We think we found one of those fragments at the Apollo 14 landing site in one of the Apollo 14 samples. And so we're very anxious when we get back to the Artemis exploration zone in the lunar South Polar region to look for more fragments of early Earth. It'll tell us what the environment was like. Maybe even we'll find specimens of fossil life sitting there on the lunar surface. So all of those are intriguing opportunities. And this is really important. When we go to the moon, obviously, we're going there to better understand the origin and evolution of the moon. But the moon is the best witness of what happened to our own planet Earth. And so by going to the moon, we are also better understanding our own planet Earth.
Well, that's very exciting, and it's also great to just hear more about how lunar science can actually affect our understanding of where our own origins. Slightly related question, but I'm curious, how much of this excitement do you feel is important that we impart to the astronauts that we're training that are going to be there? It's
utterly fundamental. I mean, in fact, this is I trained for many years the astronaut candidates, and when we came up to the impact cratering session, the very first set of slides dealt with all of these issues. You need to understand, we would say to them, that impact cratering is important for the following reasons. And amongst those was this period of bombardment. Amongst those was the impact origin of life hypothesis. Amongst those, by the way, is the modern day hazards of impact cratering processes, right? And they have to understand those deeply, not only because that enthusiasm will help them do better science once they're on the lunar surface. They are inevitably in conversation with the public. And the public is going to be asking them those questions. And so they have to be experts at some level in all of the topics that we've been discussing.
Well, you touched on this for a second, and I don't know if it applies to the moon or not, but what is the impact origin of life hypothesis?
Oh, it is that early in Earth history, when that period of bombardment was occurring, when the largest of those impactors were completely vaporizing seas, making conditions untenable for life at the surface, those same impact events were generating these deep subsurface hydrothermal systems below the floors of craters. And those environments is where prebiotic chemistry and the early evolution of life occurred. And we've demonstrated with studies at Chicxulub and elsewhere that these hydrothermal systems expand the entire diameter of these craters, that these hydrothermal systems are very long-lived, and in fact, 66 million years ago, my microbial ecosystem actually lived in that hydrothermal system. And in fact, it was the type of community that was thermophilic or hyperthermophilic, that is, it loved hot water systems, which our biological colleagues tell us is the type of community at the roots of the tree of life.
And you also mentioned, which I've always found this idea that material travels between different celestial bodies to be quite fascinating. And you touched on that there could be specimens, or we even found some stuff potentially that was Earth-related on the lunar surface. Were you also hinting at that there could potentially be ancient microbial, not necessarily alive, but evidence for ancient microbes in some of this material that might be sitting on the lunar surface?
Well, I would say that there is the potential for finding samples of these hydrothermal rocks and the potential for finding fossilized life. I do have one colleague in the UK that actually suggests that life may have persisted for a short period of time on the lunar surface. But that's a lone voice in this discussion.
Oh, very neat. And something I probably know how you're going to answer it, but I want to just run this by you, because many times we've heard this, right? That we're not going to send people out into space. We're just going to let robots do it. Oh. What are your thoughts on that one?
Yeah, humans, particularly if you're going to a complex planetary body like the moon, humans are essential, and I can say that as a field geologist, I absolutely know what I can do as a field geologist and what a robot can't do. I mean, what I can do and a robot can do are orders of magnitude apart. Now, but you don't have to believe me. So Steve Squires, who was the PI of the 2 Mars rovers, said this himself. He said it multiple times, that basically what his rovers were able to do in 6 years, a field geologist could have done in a day. Okay, so just imagine you put 2 astronauts on the lunar surface for 14 days. It would take a robot 14 times 6 years to generate the same outcome. And so if you want to get answers soon, which I think we would, you just have to put well-trained, smart-thinking astronauts on the lunar surface. And moreover, the astronauts are going to uplift, inspire, students and everybody throughout society. I mean, that is one of the big bangs of Apollo that people sometimes forget. It didn't just inspire scientists like myself. It inspired everybody in the nation because they realized if they put their mind to what they wanted to do, anything is possible. And I hear that, by the way. I give public lectures and people will come up to me and say, I'm a plumber, but man, was I fired up about Apollo, and I just every day do my best. Neurosurgeons have told me the same thing. It just had a cross-cutting, broad societal impact, and I really hope that Artemis astronauts on the lunar surface have that same effect.
Now, I guess we only have time for a few more questions here, but leaning into the human presence on the lunar surface, what's your thoughts about a lunar base and when we might have one or if we need one?
Yeah, I have to say that's beyond my area of expertise. I know that there are architectural issues related to that and sustainability issues related to that, but I have to simply say that's beyond my area of expertise. I have been asked and can comment on where a base could or should be to minimize hazards to crew, but the rationale for a base is outside of my area of expertise.
Okay, and I guess maybe the last thing would be, well, what are your thoughts on where the base should be?
You want to the impact events occur and earthquakes occur, and so one of the things you want to avoid are places where boulders might be dislodged and roll into a base. And so that's something that you just have to be mindful of. And so at the moment, that's what we're focusing on. There are other issues to be addressed. Ionizing radiation, are there shelters? Do you have regolith to sufficiently shield the moon base, and so on and so forth? But in terms of terrain, you want to be away from known mapped faults and away from high points, topographic highs with dislodgeable boulders.
Mm.
So I guess my last 2 points are, first is, are mobility systems part of your purview, whether they're human ambulatory or rovers or something else?
Mobility is important. In fact, this is one of my biggest disappointments of the Artemis program. In Constellation, we fed off of the lesson of Apollo, and Apollo taught us that mobility is king. You just have to have it. Constellation was going to land 2 pressurized rovers on the lunar surface before crew landed, and I still think that that's the right answer. I'm disappointed that Artemis isn't following that playbook. We did 4 years of lunar mission simulations in northern Arizona, testing unpressurized and pressurized rovers and how they affected scientific productivity and risk to crew. And I can't give you the precise numbers because it's been several years, but it was something on the order of enhancing scientific productivity by the crew by close to 60%, while also reducing risk to crew by about that same number. So we just need to get the mobility assets on the lunar surface as soon as possible, and pressurized rovers trumped unpressurized rovers every time.
All right, Team Space Show, you heard it. Time to write your senator. My last question here is, can you talk about some of the training opportunities that you and USRA have created for early career scientists and the International Artemis Program partners, a lot of whom are looking for ways to get engaged?
Yeah, so we have 2 different types of training programs here. I mean, in addition for the astronauts, but for graduate students, we have a program here in Houston where we bring them into Houston. We expose them to some of these human exploration elements, and ask them to help us evaluate some of these landing sites. And so the graduate students are the force behind a lot of the landing site and astronaut EVA planning that we've been speaking about. And then it's really important to introduce planetary scientists to field geology. This has been a huge change. when Gene Shoemaker was leading Apollo, every scientist on that team was a field geologist. That was required at that point of time if you were to get a geology degree. I'm old enough, that's how I was trained. But now, many geology departments no longer require field geology, and planetary scientists can go their entire career and never do any field geology. And you have to be expert in field geology if you are going to help the astronauts work well and work safely and productively on the lunar surface. So we have field training programs at Meteor Crater, in volcanic fields that are lunar analog sites, and both of those types of programs have been immensely successful. We've had hundreds of graduate students go through them. And we've then reached deeper to earlier parts of the career, to high schools. We're trying to encourage high school students how to do research, and we've helped another 600 students do research in high schools scattered across the country. So over the past few years, we've helped train a little over 1,200 students, and it's been very fulfilling.
Well, before we go, I just want to see if there's anything else you want to discuss, or do you have any books coming up, big papers you'd like to talk about, anything of that nature?
Oh, no, hopefully in your audience has heard the enthusiasm that carries me and the work that the people behind me are doing. Once we get on the lunar surface, it's going to be extraordinary. But we have to have well-trained people supporting the crew, and the crew themselves have to be well-trained. And then we have to overcome some of the architectural impediments. We do not have a credible lunar sample return mass capability. We don't have credible communication architecture. We don't have mobility architecture, as we've already discussed. And those are issues that just have to be addressed, and the faster that they get addressed, the better our work on the lunar surface will be.
All right. Well, David, I want to thank you, and Rick, I want to thank you and thank our audience for joining us today for episode number 224 that we're calling The Science of Artemis. David, what's the best place for us to keep up to date with your work?
I would go to the LPI, USRA LPI website. So type into your browser Lunar and Planetary Institute, and you'll have an opportunity to connect to a lot of different opportunities.
And I would just add, it's worth checking out the USRA, the University's Space Research Association, and look at their website, just at the broader breadth of what they're doing, because it's really sensational. Rick, where can we stalk you and your work online?
Awesome. Have a look at www.expandingfrontiers.org and also nss.org.
All right. That was brief and compact. And of course, you can always find me at pilebooks.com or at astromagazine.com, or indirectly at nss.org as well. Remember, you can always drop us a line at twist@twit.tv. We welcome your comments, suggestions, ideas, questions, and of course, space jokes, because as you can tell, if you're a regular listener, we're always a little shy on those. New episodes of this podcast publish every Friday in your favorite podcatcher, so make sure to subscribe, tell your friends, give us reviews, and like us or love us. We'll take whatever you got. You can also head to our website at twit.tv/twists. And you can follow the Twit Tech Podcast Network at Twit on Twitter, and on Facebook at twit.tv on Instagram. Thanks, everybody, for coming. It's been a real pleasure, and we'll see you all next week.
Hey, thanks for tuning in to Twit, your tech hub for intelligent, thoughtful conversations. If you want to take your experience to the next level and support what we do here at Twit, say goodbye to ads and say hello to Club Twit. With Club Twit, you unlock all our shows ad-free. You also get exclusive members-only content. We do a lot of great programming just for the club members. You also get behind-the-scenes access with our Twit Plus bonus feed and live video streams while we're recording. And don't forget the fantastic members-only Discord. It's where passionate tech fans like you and me hang out, swap ideas, and connect directly with all of our hosts. It's my favorite social network. I think you'll like it too. Club Twit. It's not just a subscription. It's how you support what we do and become part of the Twit family. Your membership directly supports the network, helping us stay independent and keep making the shows you love. If you're ready to upgrade your tech podcast experience, head to twit.tv/clubtwit and join us today. Thanks for being here. And I'll see you in the club.